So today's first Muddiest Points question dealt with what the design of the data path was and what it's doing. So to first talk about this, I wanted to talk about the MIPS instruction format again. Remember, we have two instruction formats. We've got a register-to-register format, which takes an opcode, the destination register, and two source registers. There's a little bit of extra room in the register-to-register format, so we have an extra function code here that we'll use when we're designing our instruction set architecture. The other instruction format is the immediate format, where we have an opcode, a destination register, one source register, and an immediate section that is a constant value. So this is data that's provided inside of an instruction. It allows us to get information into the program and allows us to calculate it to use it in calculations as we go forward. The first type, register-to-register instructions, are instructions of the type AND, OR, XOR, NOR, ADD, SUB, and set last then. And note that these don't have the I's on them, so they're not immediate instructions. They use the register-to-register instruction format where we provide two inputs in S and T and a destination of D. And these are addresses to registers. We have an extra function code area here that we'll use in our ISA design. The process for register-to-register instructions is to read the source operands from the registers, that's the RS and RT. We execute one of these operations using the ALU, then we write the result back to registers, given this is the destination address that we write back to. So in our blank data path, the instruction memory holds the instruction, and the instruction is encoded like this in binary, where the function is the lower 5 bits, the next upper 3 bits are the target address, one of the source addresses, the next upper 3 bits are the next source address, and this is the destination address and the opcode. And that's what's encoded in instruction memory here. This is read out, this is addressed by the program counter, so the program counter is 0, we're getting the first instruction, and this splitter here is breaking out each of these sections. The first 5 bits are broken out on this top splitter, the next 3 RT are in the next one down, then RS, then RD, and then finally the opcode here. So to execute this process, we have to connect the addresses from the instruction, these addresses from the instruction, to the register stack, and we have to connect the register stack to the ALU so that the operations that are read out can go into the ALU so it can execute its operation, and then the result of the ALU has to be copied back into the registers. And if we look at the data path, we just hook up each of the source addresses split off from the instruction, the destination address, and then the source and data into the ALU, and then the result is copied back into destination. And that's exactly what we do. You can see we make the connections here, pass them through, so these two addresses go to the register file. That causes these two to be updated and passed to the ALU. The result is brought back in, and it's written to whatever the destination address is. For the immediate instruction types, they follow a similar format, except that the function and last destination address is replaced by a constant. And those are the AND-I or ADD-I or sub-I instructions. We don't have an less than I, that's a typo. And the process here is that we read the first source operand from the registers, that's this source here. We read the second source operand from the instruction, which is this immediate part here. We execute the operation in the ALU, and we write the result back to the registers. Now in this part, we want to do a separate split, so we're copying that line and splitting out the lower 8 bits, which are this part of the instruction here. So this is the lower 8 bits, and we need this to go, since the S is this first source 1 address, which goes here, we need to be able to switch in the immediate constant from the instruction into the B argument on the ALU. To do that, we use a little mux like this, where we take the immediate constant part of the instruction and switch it with the source 2, so that when we get an immediate instruction, we can set the immediate signal. It switches to taking input from immediate rather than the register file, and we can do things like add a constant to some element in the register file and write that back into the system. That's the only change that we need to make here. For the LW instruction, things get a little more complicated. The first source operand should come from the registers. The second source operand should come from the instructions. So just like an immediate instruction format, we're using the execute operation or the add operator in the ALU to calculate the word address, because what we do is the first source operand is a pointer to a location in memory. It's an address. The immediate value is an offset to that pointer. We add those two together, and that's how we calculate our word address, which is what we use in the data memory to write, to read the word from data memory and write the result back to registers, right? So in this case, we want to be able to, we're going to use the immediate format, so that gives us our offset. The source data comes back in. For the LW instruction, the immediate is the offset to our address, source 1 is the pointer or base address, and the result is going to be an address. So we're going to connect that to our data memory. So we can connect the result of the ALU to the data memory. Then whatever we access from data memory, remember load word is a load whatever word is at this location into a destination address. So we're going to copy that, take from data memory into the destination data. Now, destination data is already being driven by the result. Right now, the result is an address, not data. So we need to be able to switch out that address and be able to write that in there. So we put another MUX on this line, just like this, that allows us to control where the source of the data is, whether it's from data memory or whether it's from the ALU. And we call this our load word bit, control bit. So when we're executing a load word, we need to set the immediate and the load word signals in order to properly execute this. Next we have the SW instruction, and this one gets a little more complicated as well. We read the first source operand from the registers. We read the second source operand from the instruction, so this is an immediate, again, where we have a base address and then an offset, which gives us the word address. We also need to read the data from the registers, because the source copies from the registers into data memory. To do this, we've only got one source address. We're actually going to use the destination register as an input register, so that means we're going to have to switch this destination bit, or destination address, into one of these source addresses on the register file, and then we write the word to data memory. So the way that this works is that we have to switch out this destination address for our source 2 address, because the source 2 data is getting switched out by immediate. We want to be able to provide this to the data memory, so that whenever we're using the immediate, whenever we're doing store word, we're going to be using the immediate for that offset. So that B argument is basically disconnected, and we can use the source 2 address and the source 2 data connection to retrieve something from memory and pass it to data memory. To do that, we're going to need a MUX on this side, and we're going to have to connect this data block to the data memory. So we place another MUX here and connect to data memory, and that gives us a path from the register file into data memory so that we can store a word. For the branch instruction and also for the jump instruction, we need to read, the way this works is the two operands are our comparison, so we're going to have to use the destination again as a source instead of a destination. So we're comparing these two, then we read the data from the register, so that's going to give us something on the ALU, and the 0 signal is going to tell us whether or not we can write the immediate value to the program counter. So in this case, the jump instruction does something much more simple, where we need to write an immediate value to the program counter always. So the way that we're going to do this, to do a branch and a jump, is to make sure that we can take a value, take two values from source, which we've already got with the source SW instruction, and when this is 0, we want to be able to write back to data memory. So we'll have a connection here from immediate to the input on the program counter, and we'll be controlling this LD signal here. If it's a jump instruction, J will be 1, and it'll automatically load into the program counter. That'll happen anytime. But if it's a branch instruction, we're going to be conditional on the 0. So if branch is 1, if this is a branch instruction, and 0 is true, if they're equal to each other, then the program counter will be set and the system will jump to a different instruction. Right? So doing all of that, connecting all those things, gives us all the signals that we need to control in order to make sure that all of these things happen automatically, because we don't want to do them by hand. We wanted to design a control unit that does it for us. Next, we filled out a table of instruction codes. And what this does is it allows us to list all of our instructions, what format instruction type they are, and what each of the pieces of each of the signals of the system need to be doing in order to fulfill that instruction. For example, to do AND, we have to set the ALU, to do the register to register AND instruction, we have to set the ALU operation control signals to 000, which corresponds to the AND operation, set sub to 0, reg write to 0 so that the result is written back to the registers, and all the other control signals to 0. For immediate version of the instruction, we have to set the ALU op to 0, set reg write to 1, and set the immediate flag to 1 so that the second operand for the AND instruction comes from the instruction word rather than from a register, and we set everything else that way. Similarly for all the rest of the instructions. The reason why we use a func code is not only because we have it, but because the 4 bits in the opcode doesn't allow us to do all 17 instructions. So we split it up by the register to register instructions, which are all of these, operations. So these are all the register to register operations. We assigned them an opcode of 000 and distinguished them by using the func bits, which are only present in register to register instructions. All the rest of the instructions have a dedicated operations code, which we can use to calculate different signals that we need to generate for these things over here. So to distinguish between the register to register instructions and the immediate type instructions, we generate a signal called the R signal, which basically detects whether all of the bits in the opcode are 0. If they are, then we use the F code to set up the signals for the operation. In this case, we use the direct encoding of ALU and sub in the func bits in order to generate those signals. So we don't have to do a whole lot of logic. We basically say if the R bit is set based on the opcode, then the first 3 bits are copied into the ALU, and the last bit is copied into the sub, and that generates all of our signals here, and that's how we got the func codes. For the rest of these, we tried to do something similar, where the first 3 bits of the opcode are the encoding of what the ALU operation was. And that works all the way up to load word. Here we've got AND is the first 3 bits, and to distinguish it between the R to R opcodes, we put a 1 on the end. So the first 3 bits of AND, of the opcode for AND, are the ALU op. Same thing for OR, XOR, NOR, ADD-I, and sub-I. If you notice that we're still doing an add operation for AND-I and sub-I. For LW, we do need to do an AND, but we've run out of codes that are able to do, we've run out of spaces that we're able to encode the control signals into the operations code. So we're going to have to implement logic that generates the control signals for the LW, SW, jump, and BEQ instructions. We just started incrementing instructions as we went for the opcode. So now that we have the table of signals built, we have to build the logic that controls those signals, right? We have a relationship between the opcodes and func codes and the control signals. This A2 is our most significant bit in the ALU op instruction code. So this is, of the 3 bits that make up the ALU, this is the ALU operation. This is the most significant bit. So this is the rightmost column or the leftmost column of the ALU opcodes. And all I've done is strip it out so we can work on it individually. And I've only listed the non-zero opcodes here because for all the other instructions that we have available, the opcode is 0. So first we need to build a 0 detector for the opcode. And that's really simple. It's something we're going to call R, which is for a register-to-register instruction. And that means that we're going to, we just have to NOR all the opcode values together, which is 03 or 02 or 01 or 00, all NORed, right? And we know from our design that if the opcode is 0, we can make our A2 signal equal to R and the F value, which we don't have listed here because it would be the upper part of the instruction set, but the signal we can AND it with is F3. So basically R is a gatekeeper. If all of the bits of the opcode are 0, then R goes high and we use the F codes instead. Now, for the rest of the A activation, we have to do a little bit of logic to fill it in. So the remaining part is from the opcode itself, where the opcode is non-zero. So what we do here is we just go ahead and we're using the opcode as the input to a K-map, and we fill in whatever the corresponding spaces are. So here for 0000, that part is taken care of by RF3, and we can put a don't care in the K-map. For 0001, A2 is 0, so 0001, that's 0. For 0010, that's this one over here, that's 0. And then we skip, notice we skip 0011. So we put a don't care there because it's not actually in the list. For 0100, it's a 0. For 0110, that's this one over here, that's a 0. And then the rest of them, and we sort of count up from there, and we've got some don't cares in there. We've got 1000, that's this guy here, that's a 1. 1001 is a 1. 1010 is a 1. 1011 is a 1. 1100 is a don't care. Sorry, that's a don't care. 1100, and then a 1101 is a 1. And everything else we fill in with don't cares. Now that we've got the K-map filled, we can start making groups. And if we look at this, the biggest group that I can make, capturing the most ones, actually all of the ones, is this group right here. And the reason why we can capture it and not worry about the rest of them is these X's are don't cares. We can let them be zeros. As long as we capture all of the ones that are specified in the list, we don't have to worry about it. And if we're and the expression that we get from this is our 03, which we use for A2, right? So this is the total expression for A2. Now let's do A1. For A1, we do the same type of calculation. We know that when we were designing the instruction set that the R gates on the middle of the F code, so when R is 1, that means the opcode is 0, and we can use the F code. The corresponding F code in our design was F2, so we can do R and F2, and then we have to figure out what drives the A1 signal from the opcodes. So we've got the A1 column from the non-zero opcodes here, and we just go through and do the same thing, filling in the K-map. So our 00 is don't care because that's taken care of by the F2 here in the expression. 0001 is a 0. 0010 is 0. We don't have a 0011, so that's a don't care. 0100 is 1. 0110, so we've skipped all the way over here, that's a 1. Then 1000, that is a 0. 1001 is a 0. 1010 is a 0. 1011 is a 0. 1100, don't care. 1, 1, 0, 1 is a 0, and everything else is don't cares. Now that we have the K-map filled in, we can start looking for groups in this one as well. And here we notice that we can make one big group around those 4 right there that captures all of the ones in the diagram with the largest possible group. And we don't care about the rest of the X's or the zeros in the loop. And of course, the diagram for this is a not 03, 02. And that gives us a not 03, 02. So all you have to do now is do this for the rest of the signals, a 0, S, sub, things like that. This is what we did in class, so you should already have the expressions in your notes. You just have to implement them in the control unit, hook the control unit up to the data path we built in class, and you'll be off and running. Okay?